I'm going to start with a bunch of derivatives. I'm going to list the old ones too, because you guys are going to be responsible for basically anything that's happened in Chapter 3 so far. So we're going to start by listing all the old ones, then we'll list the new ones. And I'm going to write chain rule versions, if that's cool with you guys. And then you can see, did we do the nested U with a couple sections? I think we did, right? Yeah, okay. Okay, so first thing, I'm going to write product rule and quotient rule, because that's, a lot of the test is just going to be derivatives. Like, I think at least a whole page is just going to be like, take derivatives. It's going to be some of the old ones, a lot of the new ones that you guys did in 3.8, 3.9, and then you should be able to combine them with product rules, quotient rules, chain rules. So like any and all of the above. So just a reminder on product and quotient rule. Okay, so you'd have the first and then times the derivative of the second, plus the second times the derivative of the first. I still see a lot of people doing fake product rules, like just derivative times derivative. So be careful with that. Okay, and then quotient, low d high, so g times f prime, minus high d low. And then all over low, low, so that would be like g of x, whatever the denominator is, quantity squared. And remember with product rule, quotient rule, I use that phrase simplify to your level of comfort. If you don't want to simplify anymore, then don't. As long as you get like the calculus done and you get it into the quotient rule, you're okay like that. And then I know that the chain rule is also in like the new category, but I'm just going to write it here because we're kind of in the area of like having some of our generic rules. So chain rule, main function, nested function. So f represents the main, g represents the nested. When we take the derivative, we take the derivative of the main. Whoops, so that would be g prime. Leave the nested function in place, then multiply by g prime. So I see, when I walk around, I see a lot of people that replace the nested function with its derivative, like f prime, and then they plug in g prime. You don't plug in g prime. You leave the g prime. I'm sorry, you leave the g, do the derivative like around the g, then multiply by g prime. I see way too many people replacing the nested function with its derivative. So I have to look like that. Okay, so those are our like 3 kind of extra rules that we use in combination of a bunch of different functions for. So are you guys good with these 3?
Yes.
Yeah.
Do you combine f prime and g prime with x, if you can?
If, like, are you saying like right here?
I'm talking about in the third one.
This one? Usually you can't. Like if it's a composite function, it would be something like sine of x squared plus 3. Or something like that. So there's really not anything that you could do to combine. Anything like that question could apply to product rule, quotient rule. If there's anything you can do algebraically to simplify it down, do that. Like if you can avoid a product or quotient rule, avoid it. Like if it's a polynomial times a polynomial, you could FOIL it rather than doing the product rule, for example. Or if it's like, you know, x squared, etc., all over x, you could divide them all by x and simplify instead of doing a quotient rule. But with chain rule, there's really not much of a way that you could simplify it because this isn't f times g. It's f with g plugged in. All right, any other questions? Good. Okay, so I'm just going to give you guys a list of all of our derivatives, but I'm going to do them in chain rule form. So first one, power rule. So we're going to write u to the n. So I'm going to write over here, and this applies for every single one. Every time I write the letter u, that is representing some function of x. Okay, so that starts now, and that's going to be all the way down. So u could be, you know, sine of x, or e to the x, or x squared plus 7, like anything that could be a nested function. So if you have a nested function raised to a power, when you take the power rule, the n comes out front, you leave whatever that nested function is in place. Power drops down 1 power, so n minus 1, and then you multiply by u prime, which would be the correction factor. Okay, So that's the chain rule version of the power rule. So again, this could be like sine cubed, or like any other function plugged in with a power. You do the power rule around the nested function, then multiply by its derivative. Okay, all the trig ones. Sine of u, so some sort of nested function. What's the derivative of sine? Cosine. Good, so all of these, like, you're responsible for all of these for a very long time. Not like, oh, I learned them in chapter 3 and now I get to forget about them. These could come up at any point from here until May. And obviously you absolutely need to know them for the AP test. After May, whether you choose to remember them or not is up to you. But you are responsible for all of these all the way through the year. Okay, so this is cosine. Leave the u in place. And then you multiply that quantity times u prime. I'm just separating those out because I don't want you to think that the u gets multiplied by u prime. It's the whole cosine expression that gets multiplied by the u prime. Yeah?
So is the u basically anything other than x?
Anything other than x, any sort of nested function. And it could be x, because say we did sub in an x right here, what would the derivative be? 1. Yes, that would be like cosine of x times 1. So this is any sort of other function besides just an x. Okay. Cosine. What's the derivative of cosine? Negative sign. Good. So if we have some nested function here, we have negative sign, the nested function stays in place, and then we multiply that expression by u prime. Tangent? Secant squared. So secant squared, the u stays in place, whatever that nested function is. Then we multiply by u prime. Cotangent? Negative cosecant squared. The u stays in place. Multiply by its derivative. Secant? Tangent times secant. Good. So we'd have tangent of u, secant of u. So that nested function gets plugged into a couple different places. So you've got like this is one quantity, this is one quantity, and then times u prime. And last regular trig, cosecant. Whoops. Little off. Negative. Good. Negative cotangent, you'd have this u plugged in. Cosecant, u is also plugged in, and then times u prime. Okay, you guys good so far? Okay, so you had power rule, we had product, quotient, and all the trig rules. That's what you guys had up until like that point where we ended on the test with chapter 3. So then in 3.8 we did inverse derivatives in general, which I'll do in kind of a separate thing, and then we had the inverse trig derivatives. So sine inverse of u. And that's where I had all those stupid little memory tricks, like the, you know, sine and secant have square roots and subtraction, all that stuff. Secant sucks, yeah. So sine inverse, we have 1 over, and then remember sine and secant have square roots and subtractions. This would be 1 minus. In the non-chain rule version, this is just an x squared, but in the chain rule version, we plug u in there and then times u prime. What's the only difference between sine inverse and cosine inverse? Negative. Good. So I'm going to write that one, but really you only need to memorize 3 of them, and then just remember that cosine, cosecant, and cotangent inverse are just the negative version. So it'd be a -1, and then everything else is identical. Okay, so those two go together. Tangent. Tangent inverse. Remember, sine and secant have square roots and subtraction. Tangent has neither. So we have 1 over. That's secant. u squared plus 1 or 1 plus u squared, because addition is commutative, and then times u prime. So all of them are going to have that times u prime. If it's like a really simple function that doesn't require the chain rule, and you have an x plugged in, the derivative is just 1. So technically you could always use these formulas. Okay, and then same as cosine, the only difference between tangent and cotangent inverse is the -1. So you guys, because I'm going to switch my page. So you guys good with this? Okay, good. Okay. So cotangent inverse. So I'm just going to carry this line down. So we still got the two columns, f and f prime. So cotangent inverse is just a -1. And then since these are ratios, you could put the u prime in the numerator. It's just, I don't know. I don't know which one makes more sense to you. Rather than multiplying by u prime at the end, you could stick it in the numerator. Okay, two more. Secant. Sine and secant have square roots and subtraction. What else does secant have? Absolute value. Because secant sucks. Good. And then the order flip-flops. Notice the sine inverse is 1 minus u squared. Secant inverse has u squared minus 1. And then since you have that nested u, you multiply by u prime. Can you guys see this okay? Like, I'm afraid if I turn the light off, then the camera won't work. Is this? Okay. Okay, and then cosecant, same difference here, is you've just got a negative. Everything else is the same. Okay, so that's 3/8. You guys still good? Okay, and then 3/9 we did the log and exponential. And then that's the end of our new rules. So old rule, e to the x, but I'm going to write the chain rule version, right? E to the u. What's the derivative of e to the x? E to the x, best derivative ever. So when you take the derivative, you've got e, you leave the nested function in place, and then times the nested derivative. This is one that people mess up all the time. And I don't know if it's because it's too simple, but people get super freaked out by it. They try to like do something strange with the derivative. You still keep the e to the u part. It's just that you would have a u prime. So if it's like e and the power is sine, it'd still be e to the sine, then you'd multiply by cosine, which is sine's derivative. So chain rule version might help. We had general exponential, so some sort of other base besides e. And this formula does work for e, but we can write a more specific version for e. Do you guys remember the little coefficient that this one has? ln. Good. It's got natural log of the base out front as a coefficient. Then it has the b to the u. And then since u is a nested function, we multiply by u prime. So this is the general version. This is the specific version. If you plugged e in here, what's natural log of e? 1. So really this works for e. We just can kind of write down that version separately because it's a special case. Okay, natural log. I'm going to write natural log of u. So what's the derivative of just natural log of x? 1 over x. So the chain rule version, we do 1 over u, put whatever the nested function is in the denominator, and then times u prime. And you might see it listed as like u prime over u, which is exactly the same. Okay, and then our very last one would be the general logarithmic with some base besides e. So that's a b down there. It kind of looks like a 6. So this is really similar to this. It's 1 over, but then we have the natural log of the base as a coefficient in our denominator. And then if it's just x, this would just be an x right here, but we're doing chain rule, so we have our u, and then times u prime. Okay, everyone good so far? So that is the entire list of derivatives that you have. Some people are having a lot of trouble with the natural log and the exponential ones. My advice is the sooner you have them memorized, the sooner you'll be able to work with them, because you need to be able to work with these in product rules, in quotient rules, in chain rules. So there will be a big part of the test that's just taking derivatives, taking all these derivatives that you know, combining them in product rules, quotient rules, and chain rules. So just a couple things, because I'm going to go into detail on implicit differentiation, inverse derivatives, and logarithmic differentiation. First thing I want to mention is like some things that you should still be able to do. So you should still be able, let's see. Okay, so two big things that you should still know how to do. You should still know how to use product and quotient rules. This time you'll just be using them in combination with like the new rules that we learned. And then you should still know how to write a tangent line. So I'm going to write a little extra something for that. Sorry about that vertical line. I got a little overambitious with the chart.
Is the tangent line y minus the original?
Yeah. So that's, we got y minus y1 equals the slope and then times x minus x1. So these, like all these different pieces, this will be given to you. So they'll say, you know, find the tangent line to f of x equals, they'll give you a function, and then at x equals -1 or whatever. So they'll give you this. How do you find this? Plug it in where? To the original function. Good. So you plug whatever the x is into the original. Plug x into the original function. And that's something you guys have probably been doing since like Algebra 1, but people get all this calculus in their head and they forget how to do the easy stuff sometimes. This slope is a big thing because here, let me write here. I still see a lot of people that just try to take the entire derivative, like a whole function, like just whatever f prime of x is. People are plugging entire functions in here. You can't plug entire functions in there. This should just be a number. And you get that number by plugging x into the derivative. So plug x into the derivative. Okay, so this should be a number, not a function. Even if it's a weird number, do you guys remember the one we had like 3 to the 18th? You'd have like 3 to the 18th or like e to the -4th or some sort of other weird, irrational something, but it's still just a number. There shouldn't be any variables in whatever you have right here.
You plug the x1, like the number.
Yep, so this will be given to you.
Yeah.
Take the derivative, plug that number into the derivative, and then clean it up and you'll have the slope. All right, so you guys good on tangent lines? And then remember with implicit, if you're asked for a tangent line to an implicit function, they'll give you the x and the y, which is like, you know, something little free and extra. So we're going to go over implicit right now. So you guys good with this stuff so far?
Yeah.
So these you need to be able to know how to do. So like I said, there's going to be a huge chunk of the test that's just taking derivatives. All sorts of different combinations of things that you should know how to do. And then we've got 3 other topics that I'm going to go over. We've got implicit differentiation, inverse derivatives, and logarithmic differentiation. Okay, so let's actually go backwards because this is fresh. Logarithmic was just yesterday. Did anyone tell people yesterday that you guys were doing logarithmic differentiation in math class? Because that sounds way more impressive than it is. You should. Is it because you wanted to keep all your friends? That's fair. Okay, so logarithmic differentiation is 2 cases. One where you have a quotient that's so ugly that the idea of actually doing it by hand is heartbreaking, or a situation where you have a variable in the base and a variable in the exponent, like x to the x, or we had like x to the sine x, or something like that. So technique goes like this. Take the natural log of both sides. So you'll have like ln of y equals, and then ln of whatever else you have on the right hand side. Then use your log properties to get everything all nice and cleaned up. Okay, so we've got the first one tells us that if you have a product on the inside, you can split it up as addition of 2 separate logs. So you could do that with like big expressions, like if you had like an x plus 3, x squared minus 2 or something like that. You could split it up and take the logs of both pieces. If you had any sort of ratio, the second property tells us that a quotient on the inside, you can split it up as subtraction of two separate logs. And then the last one says if you've got an exponent on the inside, you can move it out front as a coefficient. So basically you should get yourself to the point where you have however many different natural log expressions and you only have one thing plugged into the inside. So you shouldn't have quotients on the inside, products on the inside, exponents on the inside. So once it all looks like the right-hand side, then you take the derivative of both sides with respect to x. And then when you're doing this, keep an eye out for chain rules. So something like this, if you had like the natural log of x cubed or something like that, I saw too many people yesterday just doing 1 over x cubed and then leaving it. That's the first part, that's the derivative part. Don't forget about this. Which I guess in this case, sorry, I should have made that something like an x cubed plus 1, because if it was this case, then you would have just moved the 3 out fronts. So let's pretend it was something more complicated, like a plus 1. Do you guys see what I'm saying? If it was just an x cubed? If it was just an x cubed, I would use this property and move the 3 out fronts. But if you had something more complicated, then you couldn't split it up. So that would end up being this. Just don't forget about chain rules. Questions on logarithmic differentiation? No? No? Okay, so the day before that, actually the day before that we just did like the log and general exponential. Before that we did the inverse derivatives. So I'm going to walk through that. So not inverse trig, but the day before that when we had like the f of x and g of x. F is the, or g is the inverse of f. So here's the setup. Here's what they'll give you. They'll give you f of x, so that'll be some sort of given function, and usually it'll be something complicated enough that you can't find the inverse by hand. That's kind of the point. Is we had one that was like x plus cosine x. We had something that was like, a cubic power that you couldn't actually get the x by itself, things like that. So f of x will be given. They will tell you that g of x is the inverse of f. So if you don't see something like that, like either the notation or the words, like if you don't see anything about inverse, chances are you're not using this technique. So I wouldn't ever just like make up a scenario, be like, I think I'll use inverse derivatives here. Like make sure it's actually telling you something about inverses. And then what they'll ask you is to find g prime at a certain point. So that's usually the end goal of one of these inverse derivatives, is to find g prime at a certain point. So remember, g is the inverse. They want the derivative of the inverse at a certain point. Okay, so that's what you'll be given. That'll be the setup of the problem. So let me kind of walk you through the logic that you'd use to figure these out. So from this, knowing that they're trying to find g prime of b, what you know is that b, whatever that is, they might give you like 6 or 4 or whatever. We know that b is an x value on g. So it's just kind of known. Just by this notation right here, we know that that b must be an x value on g. You guys agree with that? So what do we get for free? Like if we know this, what else do we know? It's the y value on f. Good. So that implies that b is a y on f. Okay, so then knowing that b would be a y value on f, we're going to take our function f of x, set it equal to b. And then this is where I told you guys to do that like look at it method. They'll usually be pretty low numbers, that it's going to be like 0, 1, -1, something you could just kind of look at, because it's not something that's solvable by hand. If it was solvable by hand, you could find the inverse by hand. So they're going to be like nice and easy numbers that you could just kind of figure out what it is. Solve for x. And let's call whatever that value is a. Just kind of using generic notation here. Okay, so now here's what we know. AB is a point on F, which means BA must be a point on G. And remember that little Greek lowercase epsilon, that's the, it means like is an element of, is a point on. Okay, so I know this is all very generic, but are you guys good with what we would have figured out so far up to this point? Okay, so now our goal is to find G prime of B. So what we do instead, because we have this information, we find F prime of A, and then how does G prime of B relate to F prime of A? It's the reciprocal. Good. So if we want G prime of B, what we do is we find F prime of A and then take the reciprocal. So what I mean by this is we find F prime, like as a function, and then plug in A.
So it would be 1 over F prime of A? Or
Yep.
F prime of A?
Exactly. So G prime of B would be equal to 1 over F prime of A. So basically, like, if you guys want one thing to memorize for this section, memorize this. Like just this little ratio right here. And then if you can remember how you would find A relative to B. So maybe memorize this and maybe like toss this in here. If you've got, whatever you got room for. Yeah.
Is there another formula that's the exact same thing as that?
There is, they write it in a slightly more complicated way. Like this is the way the book writes it. 1 over F prime of G of B. The book writes it like that. And G of B is A. Like that. Oh no. Giraffes. Okay, airplay. Is it back? Hooray. Okay, we got this. Okay, so yeah, the book gives us this. So like G of B is A according to this. But if people are like, how do I find G of B? Well, that would be the Y value on G, which means it's the X value on A. So I think this is a little simpler. So if you know this relationship and you memorize this. What's that?
Your iPad is bouncing.
Yeah, I know. It does that all the time. Okay. Any issues, any questions on inverse derivatives? Okay, so our last thing is implicit differentiation, which also sounds very fancy. Oops. Okay, so implicit differentiation, that's when the x's and y's are just all kind of mixed up and you couldn't separate them if you wanted to. Like if you can't get the y by itself, you'd have to use implicit differentiation. I wrote differentiations, that's what that is. It's just me trying to get rid of an s that doesn't make sense. So that's if x and y can't be separated, then you would use implicit.
Will these be sectioned out? Like you'll say use implicit differentiation?
I don't remember if I did write that or not, but you should be able to recognize them. Like if it's like x squared plus 3y squared plus 6xy, like if they're just all jumbled together. If it's y equals and then everything's on the other side, then it wouldn't be implicit. They should be pretty easy to recognize. Okay, so take the derivative with respect to x of both sides. So d by dx of both sides. And then remember that means you take the derivative of absolutely everything. If it's just x stuff, then you don't have to do anything fancy. If it's y stuff, here let's write This will be very formal notation here. Y stuff. Anytime you come across y stuff, you take the derivative, but then multiply by what? dy by dx, which is like the nested derivative. That's like the u prime in the other rules that we had written down. So after you take the derivative, multiply by dy by dx, which is just the nested derivative. Y is like the nested function, so dy by dx would be the nested derivative. And keep an eye out for product rules, quotient rules, things like that. Your end goal is to get dy by dx by itself. So you would have to gather everything that does have a dy by dx on one side, everything that does not on the other, factor it out, divide to get it by itself. So before I open up to questions, I have one more example that I want to give you guys. And it's an example out of the book that I think some of you may have gotten to. It's an implicit example. So do you guys have any questions on this? Anything? Is it written down? Good?
No.
We're still copying. Okay, I'll let you go. Yeah.
Can we do, like, after that one, do an inverse problem?
Yeah, absolutely. You can pull some examples. Okay. Still writing. So if anyone has their book and wants to look, it's on page 193, the example that I'm going to do. Page 193.
Almost.
Oh no, I'm going to leave it. I'm just going to start writing the page I'm on. Okay. So the problem I'm going to do, page 193, number 41. Anyone still copying? Yeah, okay. Okay, so I am dropping a not so subtle hint your way with this problem. So here's what they give you, and then they ask you to find all points with a horizontal tangent line. Okay, so I am hoping that you see this and something just automatically springs to mind. Like what does that tell you? Slope of 0. Good. So that to us should mean y prime equals 0. Or I guess in the case that we're working in right now, dy by dx equals 0. Because this is definitely implicit. Do you guys see what I'm saying about the implicit? Like this is hard to miss. When you see something that looks like this, where the x's and y's are all kind of mixed in there in one equation, that's where you have to use implicit. So we'll walk through our steps. Take d by dx, derivative with respect to x on both sides. If it's x stuff, nothing unusual is happening at all. If it's y stuff, just make sure you have that correction factor, the dy by dx. So derivative of 3x squared. 6x, nothing unusual there. Plus derivative of 4y squared. 8y dy by dx. How about this third piece? What's going on there? Product rule. Product rule. So I would, if I were you, I would treat the 3x as the first and then treat y as the second. If you wanted to, you could kind of pull the 3 out in front of everything, but I think that opens up more room for mistakes. Opens up the opportunity to forget about the 3. So I would just leave it as the first function. So first would be 3x, derivative of the second? dy by dx. Good. And then plus the second, which is y, times the derivative of the first? 3. So I'm just going to sneak that back in there. Derivative of 24? 0. What's that? I have people that write 24 all the time. Like people will get through all of the calculus and then write 24. So yeah, make sure you're paying attention to taking the derivative of that too. So this part's just kind of the algebra, like getting the dy by dx by itself. So I'm going to leave this stuff on the left-hand side. I'm going to move the other things over to the right and then factor out the dy by dx from these two terms. So I'm going to kind of combine a couple things. You guys let me know if it's too much. So like these terms that I have underlined, I'm going to factor out a dy by dx. Leaves me with 8y plus 3x equals, and then I'm going to move these two terms over. So minus 6x minus 3y. So I kind of did like 2 or 3 things at once there. Was that okay?
Yep.
Good. Casey?
So if it was like, in from the beginning, 4y to, like, 4y cubed, would it be like 12y to
12y to the second, the dy by dx would be after. Yeah, so yeah, if there was a cubed, then you'd still have the second power, but it would be like in between right there. Okay, so then divide both sides by this term. So cancels from the left. So now we have dy by dx. Okay. If you were doing a tangent line, at this point you could plug in whatever the xy point is that they give you. We're not doing a tangent line, though. We're trying to find where certain tangent lines are. So now back here, we want dy by dx to be equal to 0. So what would we do next? Set the numerator equal to 0. Good, we don't need the whole thing. We can just set the numerator equal to 0, because as long as the numerator is 0, that whole ratio would be 0. What would the denominator tell us?
It's defined.
Good, if it's defined. So if we wanted it to be undefined, if we wanted what kind of tangent line? Vertical, we could set the denominator to 0. Good, so setting the numerator equal to 0 is our goal here. So I think, like, does this problem look familiar at all to you guys? Some of you guys got this far. Some of you guys got this far, and then it was like, okay, now what? Did anyone get this far and figure it out? Like, did anyone get past this point?
Solve for one and substitute.
Perfect. Solve for one and then substitute to find the other. So solving for y in this case, solving for y in this case is a little bit easier because then you don't have to deal with a fraction. If you solved for x, you'd have a 1/2, and that's just not fun for anybody. So let's get the y by itself. Okay, so that's our expression. So we know that any place y is equal to -2 times x, you'd have a horizontal tangent line. And so I have people that get this far and then say like, okay, so let's just say that x is 1, and so then y would be -2. All done. You can't just make things up. It's like how, let's kind of trace back to the beginning here. What would we do with this? What do you think, Charlie?
We put it in the original function.
Yeah, plug this into the original. So the people that are just like making points up, like if people are like, yeah, the point 1, -2, that would work. You don't know if 1, -2 is actually on this curve. Like this curve is defined by only a certain number of x and y points. So you just can't make up a point. You could make up a point and like plug it in and hope that it works, but that would take a very long time. So we're going to take this expression, sub it in for y. It's like right here, and then everything will be x, and then we can solve for x. All right, so this is actually like just a really beefed up version of like algebra substitution method. Just a little bit more intense. So back into the original, we've got 3x squared, because now we're trying to find all the points on this curve where y is equal to -2x. So we're subbing it in. So plus 4 instead of y squared, sub that in, plus 3x, and subbing this in for y equals 24. So hopefully you guys see what I mean here. It's now all in terms of x, so we're going to be able to solve for x. So 3x squared, this is 4 times 4x squared, so 16 minus 6x squared equals 24. And this is algebra beyond this point. So 19 minus 6, we've got a 13x squared. Oh, these are going to be some nice numbers here. This is good stuff, guys. So we've got x squared equals 24/13. And square root both sides.
So what was that about not using fractions?
This is totally fine. You guys can absolutely just leave your answer like this. If in your mind you're like, no, 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 I need to rationalize that and simplify it, you feel free. You go right ahead. Some people are very uncomfortable with unsimplified things. I actually kind of am myself. Like, that's a little bit painful for me. But the idea of simplifying is more painful for people. So this is totally fine. And then you guys actually want ordered pairs. So then we can sub back in. But all you have to do is sub back into this equation, which is super easy. So we've got one ordered pair that would be the positive square root of 24/13 for your x value. And then another one that would be the negative version. So then when you sub this in here, all you have to do is multiply it by 2, -2. So this would be -2 times that beautiful root. And then this would be +2. Anytime in Calc, my tests, AP tests, this is always preferred to a decimal. As nauseating as these values are, this is always preferred to a decimal because this is exact. Okay, so those are the two ordered pairs that answer your question there. How are we doing? See, this, you guys would have been fine if this turned out to be like 2. Like you guys did all this crazy calculus and you were perfectly okay with this. And then this, you're like, nope. No. So this is just as okay as if it had turned out to be 2, I promise you. Okay, Shannon, what did you want to see?
The inverse.
Inverse? Okay. So let me see if I can pull an example. So inverse was page like 180 something. Let's see.
So what we just do with implicit?
That was implicit. Yeah. Page 181. Okay. So page 181. We are given a value, a function, and then we are given the value that they want. Okay, so 3/8. Let's say we have f of x equals x plus e to the x, and we want to find g prime of 1, where g is the inverse of f. Okay, so that's what the setup would look like. You'd have f, they'd tell you that g is the inverse of f, and then they'd ask for a specific derivative on g. Okay, so I'm going to kind of go back and forth between what I wrote for you guys, and we'll kind of go through the steps. So this is what I wrote for you guys. The function is given. We got that. They tell you that g is the function of x, and then they ask you to find for a certain value of g. So first, we know that b is an x on g, so we know b is a y on f. So if we know that 1 is an x value on g, that means 1 is a y value on f. Okay, next thing I wrote down was set f equal to whatever that value is. So we can take x plus e to the x and then just set it equal to 1, because we know that if it's x for g, that means it's a y value for f. So this is how low those values are going to be. Like you should just be able to look. There's no algebraic way to solve for x here, but you should just be able to look at it. 0. Yeah. Okay, so what that means is that 0, 1 is a point on f, which means 1, 0 is a point on g. Good so far? Okay, so we want this derivative at this point, which means we have to start by finding this derivative at this point. And that's just calculus that you've done so far. So we want f prime of 0. So start by finding f prime. What's the derivative of f? 1 plus e to the x. Good. Derivative of x is 1. Derivative of e to the x is still e to the x. So what is f prime of 0? 2. Good. 1 plus e to the 0, which of course is 1 plus 1, and that's 2. So what's g prime of 1? 1/2. Good. Just take the reciprocal. So notice we didn't find the inverse. We don't have to, we actually can't. Like if you did x equals y plus e to the y, you would have no algebraic way of getting the y by itself. So, any other questions? Questions? Concerns? We got like 5 minutes, I could do whatever else. Always concerns? Yeah.
These problems, it was like on page 187.
187, okay.
And it was numbers 23 to 27. Like that type.
Okay, so like some chain rule with the logarithmic. Okay, so page 187. Page 187, let's do, maybe do an even one that we haven't done. So we can do, let's do number 24. Okay, so that's our function. Sorry, it's totally sideways. Okay, so that's our function. We want the derivative of that. So the variable is t. So I'm going to take the derivative of this whole thing with respect to t. So we'd write d by dt instead of d by dx. Okay, trying to find that sheet where I wrote all the derivatives. Oh, here it is. Okay, so this right here, that's our derivative rule for log base whatever. So in this case, the base is 10. So 10 would go right here. Our nested function was t plus, what was it, 2 to the t? Yeah, so that would go here, and then its derivative would go here. So I'm just going to copy down what the derivative is. So derivative, kind of the generic derivative is 1 over the natural log of b times the nested function times the nested derivative. So we're just going to sub in where everything goes. Okay, so this derivative would be 1 over natural log of 10. Remember, that's just a number. It's some sort of weird irrational number that we're not actually going to evaluate, but it is just a number. And then times u. So instead of just an x or just a t, we have a whole nested function in place there. And then times the derivative of the nested function. So we get to practice another one here, actually. So plus the, or times the derivative of this. So derivative of t, 1. How about the derivative of 2 raised to the power of t?
And then 2 times 2 to the t.
Nope, we're doing power rules. It's not a power rule.
ln 2.
ln. Good. Natural log of 2 times 2 to the t. That is, I'm just going to cover it for a second. That is this one right here. 2 to the t falls into this category. Natural log of 2 times 2. So if the base is a number, that's exponential, not a power rule. So as lovely as this is, that would be your answer. And really all you could do with that is put this in the numerator, I guess. And that's honestly, even if you did want to simplify it, there really isn't much that you can do there. So the best thing you can do for yourselves, guys, is to memorize those derivative rules. Have them memorized so you can just use them. Like if you had this memorized, then you could kind of just toss it down on your paper and then use it. So I have a review video. I emailed it to you guys already because my first hour wanted to watch it in like one of their classes that was all juniors or something. I don't remember. It's going out at 11 or at 2:30, but I emailed it to you already. So it's just the review problems. So do as many as you want, or just watch the video, or both, or whatever. Yeah, any other questions? No? Good. Oh, I'm still recording.